Hello, in this video lesson we will be discussing correlation and how to determine linear regression models. Please take a moment to read today's objectives. So by the time you are viewing or watching this video, you are probably at the point in your project where it's time to analyze the data that you have collected. One of the best ways to do so is using a technique called regression. Before we get into the techniques and show you how to do that, let's write down some simple definitions that you need to be aware of going forward. Our first definition is mathematical modeling. So you've been doing a lot of this throughout your high school math careers as well as in this class, and it is defined to be the process of using any one of words, graphs, tables, or equations to represent real-world situations. So anytime you're given a quote-unquote word problem that asks you to solve it, you are using mathematical modeling on some level. This is, again, trying to relate the real world to the mathematics. So a very simplistic example of mathematical modeling would be if you're given the statement that someone, let's call him John here, makes $12.50 per hour at his or her job, then how could we take that and model that through an equation or some other form? And so our equation would be his wages W equal 12.5H. The idea of taking those words and translating them into an algebraic representation like the equation here is a form of mathematical modeling. So you have done a lot of this throughout your math careers, and you will continue to do so. The next definition we have is linear regression. And linear regression is a specific type of mathematical modeling that you will be using as the cornerstone, basically, of your project. So what is linear regression? It's the process of creating a linear equation to model data from a table or scatter plot. So if you kind of take a look here in this diagram, we have a scatter plot, notice the points in blue, and we've put a line that comes close as possible to as many of the points that you see there. You've done this, we call this maybe the line of best fit. That's another term for linear regression. So you may have done some of this already, but you're going to need to refresh your memories here because once again, this is the cornerstone here of our project. The next definition is the least squares regression line, and it's defined to be a linear regression model that seeks to minimize the sum of the squares of the vertical distances between the data points and the regression line. Let's try and break down what this definition means in further detail because it is a very important process of our project. So let's suppose that you're given a set of data and I'm given a set of data, and we make a scatter plot of that data. We each do our own, and then we attempt to draw best fit lines that hit a majority of the points on our scatter plot. It is almost certain that your line that you draw will be different than the one that I draw because we have different perspectives and we just go from different opinions. However, this least squares regression technique takes that uncertainty away and puts the line in the same position every time based on the fact that we would like to minimize these vertical distances that are between the points and the line. So there's a little formula, so to speak, that creates this line and puts it in the absolute best position. So after the regression line is put or superimposed on the scatter plot, the next question is, well, how good of a line actually is this? This is the best possible line that can be drawn, but relative to the data set, is it still a good fit? Is it a line that we should go with, or should we try some other type of equation other than a straight line? That's where the correlation coefficient comes in, also known as the R value. The correlation coefficient is a statistical measure of how well your line or equation fits the overall set of the data. The correlation coefficient will always be a value between -1 and 1. So the closer that the absolute value of R is to 1, the better fit. So let me give you a few examples. So I went ahead and pulled up a diagram that I just searched for on Google, which kind of gives the continuum of the correlation coefficient, and it does a good job of explaining what a correlation is in terms of the R value. So please do me a favor and copy down this continuum with its labels somewhere, maybe on the back of your notes, or if you need a separate sheet, go ahead and do that. So let's start first with a strong correlation example. So if there's a perfect negative correlation, which would mean the R value is -1, then you're going to see every single point on the scatter plot actually on the line that you were able to draw. This is very, very, very rare in terms of data collection with two variables, but it is possible. So moving towards the right on this continuum, the next correlation coefficient we see is -0.5. If you were to have that correlation coefficient for a set of data, then you're going to see something like the scatter plot I've drawn above that value. Notice what you see. The slope of the line is negative, hence the negative R value, and some of the points are on the line, not too many. More of the points are off of the line, and the distance from the line to those points is not too great. So if we do have a -0.5, we're going to call that a correlation, but it's neither strong nor weak, but we could observe that as being a correlation of some sort. So as we continue to move to the right here, we are now at a 0 correlation, and what would happen in this case is you would notice that all of the points, or very, very few of them, are touching this line, and they are scattered throughout the graph, and therefore the only line that we could draw would be a flat horizontal line. Notice that does correspond with the slope. The R value is 0 because this line of fit has a slope of 0. So in this case, we would say absolutely no correlation between the two variables. So as we continue to move to the right, the next R value would be +0.5. So again, this kind of mirrors what you see with -0.5, with the only difference being that the slope of the line is positive. In other words, there's a positive correlation in this case. So finally, we've arrived at +1 for the correlation coefficient, and again, this will mirror the -1 correlation coefficient, with the difference being that the slope of this line would be positive. So remember, in the two far end cases, that would be ultimately, in our project, this would be a dream. If you could show that either of your correlations were -1 or +1, that would be fantastic, and we really we're on to something that we could investigate further. However, these are extremely rare cases. So again, take a look at this, make sure you copy it down in detail, because it will be, one of the major focuses of our data analysis once that begins. So now in example 1, we finally have a set of data in which we will attempt to use some technology to produce a scatter plot for us and do a little bit of a regression analysis. So the data we have in front of us is the population of the United States from 2003 to 2010. In Part A, you're asked to make a graphical model of the data using Google Sheets. So you're going to input this data into a Google Sheet. However, I'm not going to show you that. This is something that you're going to do when you get back to class. Okay, so Part A we're going to do in class together, and we'll put the scatter plot and we'll show you how Google Sheets can help you produce a scatter plot, which you're going to need to do for your project. But we're going to do it by hand in Part B, and we're going to do that together. So the first thing you need to do is label both axes, X and Y, with numbers and words. So on the X-axis, or T-axis in this case, we're going to put years, because that was what was given to us in the top row of the table. And then on the Y-axis, as it says, is population. I went ahead and decided to go up by 2s. I started labeling with 290 to make sure I could cover the minimum. And then I skipped a tick mark and went up by 4s, which every tick mark now would then be going up by 2s. I've labeled it with population in millions, and of course I've made a little note that 3 means the year 2003, so you can interpret that. So the next thing we're going to do is plot those points. So once the points are plotted, what you can see is, in this particular case, there is a very, very strong positive linear correlation, and you can see that by the pattern of the points. In other words, it would be very, very easy for me to try and draw a straight line that hits nearly every point, and the points that I have missed are not very far off the line. So there's an extremely strong positive correlation, and as the years or time increases, population also increases. Remember, y is the dependent variable. Therefore, we could also say that the population depends on the time. Well, in part C, we're asked to find the actual equation for that line that we sketched on our scatter plot. So to do that, you can do it one of two ways for the project. You can use the graphing calculator and or use Google Sheets. So in part C, I want you to produce the equation using Google Sheets, which if you can't do it by following the link and you don't have access to that, then we can show you also in class. But then also, I want you to try it on your graphing calculators, and that's what part D is about. So again, I want you to produce this equation using two different forms of technology and see which one you're more comfortable with. So when you use the graphing calculator to produce this equation, it will give you the same one, but I want you to know how to do it with both. So please try and use your graphing calculator to produce this equation using the data. You'll have to go to the Stat menu. You'll have to enter the time values in list 1 and then enter the population values in list 2, and then there's a sequence of keys you will press to get you to produce the equation that you see here. So please try it and check it, and I can answer any questions the next time we meet in class. So in part C, we're asked how good of a fit is the model or our line, and explain using the correlation coefficient. Well, if you remember the line that we drew on the graph, it nearly hit every point, and the points that it may have missed were very close to the line. When you produce that equation, you will also see with your graphing calculator and on Google Sheets the R value, and in this case it was 0.999. Remember, that is very, very close to 1, which is the maximum possible value. So with that, along with our picture, it's pretty easy to see that there's an extremely strong correlation between time and population. So part F asks us to interpret the slope of our equations, and in both cases it was 2.72. What that means is that each additional year we could expect about 2.72 million additional U.S. residents. So lastly, in G, we're asked to determine what the population of the U.S. will be in 2030 based on this model. And so what we'll want to do is any time that you come up with a regression model or equation, the next thing is can we use it to make predictions? And that, of course, depends on how good of a fit your equation was. Remember, in part E, we noticed that this is a very, very strong correlation. Therefore, it is very accurate and valid to make these assumptions with our equation, so we'll go ahead and do that. So if it asks us what the population is in 2030, we're going to plug in just the value of 30 in, because remember, the whole equation and even our scatter plot were set up based on using 3, 4, 5, 6, etc. for the years as opposed to 2003, 2004. So we'll plug in 30 in for the time into our equation, and we will simply multiply by 2.72 and add the additional 282 million to get us approximately 363.3 million people. So finally, in example 2, you have another opportunity with the data set to try and do the things that we did in example 1. And I do want you to spend the time to do this, because what you see here are basically just smaller sets of data of exactly everything I'm asking you to do in terms of the data analysis, and which will then, of course, advance what you can do in your presentations. So please take and pay close attention to examples 1 and 2, because again, these things are the basis of our data analysis pieces. So have that ready to check for tomorrow, and we'll go over any questions that you have. Thanks again for watching, and good luck.